Today we'll talk about a method for solving equations called the Newton polynomial factorization method. It can be used to solve problems of the following form: p of x equals 0, where p of x looks like a kth order polynomial. The question that Newton was thinking about is, well, suppose you know that there is a root x prime near x sub n. Can we use x sub n to find an even better estimate, which we can call x sub n plus 1? Newton's idea was to replace x with x minus x sub n plus x sub n everywhere, and then expand the binomial, each binomial, using Pascal's triangle and combine like terms and come up with in effect, a Taylor series expansion. Today we would call such a polynomial Taylor series expansion, but this was long before Brooke Taylor wrote about the subject. Today we would obtain the coefficients using calculus, but ironically, even though Newton invented calculus, he did not see the connection between calculus and finding these coefficients. Newton wanted to solve this problem algebraically, which is only practical for lower order polynomials. Newton argued that the first two terms of this expansion was the tangent line. And further, Newton argued that the line L is a good approximation for the polynomial because the higher order terms were small and can be neglected. So you could use L as an approximation for the polynomial when x was near x sub n. Furthermore, you could update x by solving for L of x equal to 0. That's just a simple linear equation, and you come up with this iconic formula. Let's look at a picture. We're trying to find where the yellow line, the yellow curve, crosses the x-axis. That's the green dot. So Newton's method was first pick a point somewhere on the green curve. That'll be a pink point. Find a blue tangent line to that pink point and use it to find the red dot, which is the intersection of the blue line and the x-axis. That will be your next guess. Now that we have the next guess, well, that'll be the next pink dot. We'll have a new blue line, a new tangent point, another point red dot, which will be much, much closer to the green dot. Each time we're getting much closer. Now these shortcuts we're going to talk about, you don't really need to know about them. But they might be useful if you want to use the algorithm a lot. It's possible to find the parameters a0 and a1 in terms of the original parameters. And by the way, one shortcut is just not calculate a2 and a3 and a4 because they're not used. The parameter a0 is easy to find. You can easily show that a0 is just the original polynomial evaluated at x sub n. Let's That's pretty easy to see. Now, the parameter a1 takes a lot more work. But if you expand each term and look at the term of the form x minus x sub n to the 1, you find out that that coefficient is k times x sub n to the k minus 1 times b sub k. Combining the terms, you get this formula. I would not recommend using this at first. You should solve it the long way a few times until you get comfortable. So we'll do an example. We'll do this polynomial, this cubic. We're not going to skip any steps. We'll substitute in x minus x sub n plus x sub n in everywhere. Then we will expand each binomial. You get 7 terms. Then combine like terms. So these are the constant terms, the first order terms, the second order terms, and the third order terms. Now that we have this, we can easily identify the parameters a0, a1, a2, and a3. Keep in mind that we're only using a0 and a1. Now that we have a0 and a1, we can use those to update x to make it x sub n to make it x sub n plus 1 using this formula. And you have to start somewhere, so we'll say x sub 0 is equal to s over 3. So let's go to the spreadsheet and see how this works. We'll start with the initial guess. We'll put in the formula 3x minus 4x cubed minus the parameter. The slope term is 3 minus 12x squared. The adjustment is minus y over the slope. And then we update x by adding the adjustment. We bring these calculations down, it should converge very quickly. And it does. Now, one thing to note about Newton's method is that the adjustment tends to, the natural log of that adjustment tends to increase by a factor of 2 each iteration. So the ratio of these numbers is going to be around 2. And that's true not just of this example or this parameter, it's any parameter and any problem you think about, it's going to be that this ratio is about 2. It's not exactly 2, it's just an approximation. We'll put in different values, and when we choose larger values, it converges more slowly, but it's still, the ratio does eventually get close to 2. Now let's do another example. This is a quintic example, and it's kind of messy. But it happens when you are trying to find a fifth root of a number. So we'll show you the expansion. We'll skip a lot of steps here. You can treat this as an exercise to verify all of this. So we can use that to identify a0 and a1. We'll choose x0 equal a over 5 as the initial guess, and we'll go to the spreadsheet and see how well Newton's method works in this example as well. So for this one thing to note, the parameter's name is a instead of s. It doesn't really matter. But what we will do is we'll copy all of this code from the one sheet to the other sheet, because most of it is going to be identical. Just need to make a few changes. We'll change the initial guess to the parameter divided by 5. The y value is 5x plus 10x squared plus 10x cubed plus 5x to the fourth plus 1x to the fifth minus the parameter a. Have to be careful to type all that correctly. In the slope term, this is 5 plus 20x plus 30x squared plus 20x cubed plus 5x to the fourth. Again, you have to be very careful that you type it in correctly. If you make a mistake, you'll know immediately because it won't converge to the right answer. So if we did it right, we copy this down and bring it down, we'll see it converge immediately, and it does. Notice the ratio is again about 2. We'll choose different parameters. When we choose a small value of a, it converges very rapidly. But when we choose a large value of a, the initial guess is poor and it converges slowly. All you have to do is change the examples and you can solve the problems. Well, thank you.